Um, Great. So I'm Macy Huston. I am a postdoc at UC Berkeley, working in the Moving Universe Labs, and I'm going to be talking about our project Hunting for Black Holes via Astrometric Microlensing. This is a project that was started by Jessica Liu, and I've been working on some re-reduction and some software development to refine and finish these results. Most of this data actually was taken several years ago, so before I was involved, I'm not sure if Sherry was the support astronomer on those nights, but she was on our more recent ones. So the scientific context here is that we are searching for isolated stellar mass black holes in our efforts to understand stellar evolution and the populations of black holes in the Milky Way. A lot of our science is enabled by binary systems that involve black holes where you can detect them through X-rays or through orbital motion of a luminous companion. But we are particularly interested in isolated stellar mass black holes that you can't really detect with any of those signatures, and instead we just detect them through their mass with microlensing. So just as kind of a reminder of what microlensing is, since we've talked about gravitational lensing on a couple of different scales, this animation here is showing what a microlensing event looks like when you have a luminous star pass behind a massive lens object, in our case, a black hole. And so then what we're seeing in these lower plots is that for gravitational microlensing, we can't actually resolve these individual images as they warp and move. But we can see in these lower figures that the source star will appear to brighten as the lens passes in front of it. And we'll also see an apparent shift in its position, where we're not seeing two separate images, but we're seeing the centroid of the star just appear to move slightly on the sky. So for this project, in our search for black holes, we first start by selecting our candidates from photometric microlensing events. So these come from various photometric surveys. And specifically, I'm looking at a few targets today that were identified by the optical gravitational lensing experiment, OGLE. And so we want to select those microlensing events photometrically that look like they could be caused by high mass lenses, which could be black holes. So specifically, the main thing we look for is long timescale microlensing events. So for definitely events over 100 days, and sometimes we can get events as long as 200 or 300 days for their timescales. And so we pick these best candidate events for a high mass lens, then follow them up with astrometry in order to try to break the mass distance degeneracy that you get from photometry alone. And so with the added astrometry, we have the goal of measuring the mass of the lens. But if we don't get a detectable astrometric signal, we can at least put an upper limit on what the mass of that lens could be. And so this is a lot like what Kemi was talking about earlier with his white dwarf, which is that if we have a mass measurement and we have observed limits on the lens's brightness, then we might be able to confirm that the lens is in fact a black hole. So with astrometric microlensing, what we need is the best astrometric measurements that we can get. So this involves instruments like Keck with adaptive optics, or space telescopes like Hubble or JWST to get diffraction limited imaging. And this curve here shows kind of the timescales of microlensing events, where the dashed line is the magnification of a microlensing event. So we detect these events while they're ongoing photometrically and try to pick up and start our astrometric observations while they're kind of on the downhill of that slope. Fortunately, the astrometric shift of a microlensing event peaks actually before and after the photometric event. So we can capture the peak of these events and then continue to monitor them for a few more years as that this apparent motion of the source returns just to its baseline proper motion. And then we can figure out what the size of that astrometric shift was. So this takes several years of observation for any one target. And so far, there has been one isolated stellar mass black hole discovered through this technique so far through astrometric microlensing. This was OB110462, which was confirmed as a black hole with HST astrometry. So this is from a paper by Casey Lamb and Jessica Liu that came out of our group just before I joined it. And so what we're trying to do with this project and our continued work is to add additional isolated stellar mass black holes to this population so that we can draw some conclusions about the masses of these objects, as well as natal kicks by also measuring their kinematics. So our data is adaptive optics imaging that comes from NIRC2 and from OSIRIS. So we use laser guide star imaging. For reference, most of these targets that we look at are something like a few degrees away from the galactic center. My background here actually is one of our NIRC2 images. And so most of our images come from NIRC2, and then in the spring of 2019, they switched over to using OSIRIS. And what we're aiming for with this imaging is about 0.1 milliarcseconds in astrometric precision for the brighter stars in our images. So when we have this data, we use the Chi reduction pipeline. This is the Keck AO imaging data reduction pipeline. And I've been doing this re-reduction of all of these older images using an updated distortion solution for the OSIRIS instrument, as well as an updated nonlinearity correction for NIRC2. So we plug all of our data into Chi, which will align and combine the images and then extract that precise photometry and astrometry for all of the stars in our image. So to analyze this data, we take those star lists produced from each epoch of data and use our FlyStar code to match and transform them. And so this uses the surrounding stars in the image to establish our astrometric reference frame and will output an astrometric time series for our target. We can then take that astrometry data and combine it with any photometric data from surveys that picked up this event and fit our microlensing event with the Bayesian analysis of gravitational lensing events software, or BAGEL. And so this performs a joint fitting of the photometry and astrometry for our event. And so I have a few events from the sample to talk about today. The first one of these is actually an example of an astrometric non-detection. So this event was initially studied in a paper that Jessica published in 2016 that had 2 years with 4 epochs covering this target. And there was basically a non-detection of an astrometric signal in that study. This time we have followed it for an additional 3 years, added 4 more epochs of data. And we were able to take the 99% confidence interval mass upper limit for the lens from about 40 solar masses in that original paper down to 2 solar masses with this additional data. We still have a little bit of refining to do of our models, but in our preliminary results, we're seeing an upper limit of 2 solar masses, which would rule out a black hole lens for this event. My next event is one where we actually do have an astrometric detection. So you can see in the astrometric curve here that we've got this kind of weird C-shaped path that the object follows. The blue line underneath is what that path would look like if it was just a star with a proper motion and little wiggles due to parallax. And then our red curve shows that little signal that you get from the astrometric microlensing event. So this event from our preliminary analysis, we've got a little more work to go here, but the current preferred model for a point source point lens solution is a 1.5 solar mass lens, which would make it a neutron star candidate. But as you can see in the photometric light curve, we have a little bit of weird residuals going on here. So we're also considering the possibility that either the lens and or source star in this scenario could be a binary. And those fits are currently running and they take a long time to run, so I wasn't able to show them today. We've got a couple more events in this sample that, again, we don't have final results yet for, but this is for a pretty interesting reason, which is that in our astrometry, we're actually picking up parallaxes for at least a couple of the stars in our images. And so when we phase fold our data, put it in ecliptic coordinates, we actually see these curves that are consistent with parallax in some of our stars. So I am working right now on developing our FlyStar code to account for more complex models of stellar motion that includes parallax instead of just linear proper motions. And so we'll have more results coming soon with those 2 targets. And so I just wanted to wrap up by mentioning a few things that we're also working on right now. So we recently wrapped up our observations for the past semester, where we finished up our baseline coverage for a batch of microlensing events that originated in 2017 through 2019. So one of the grad students in our group, Natasha Abrams, is going to be working on a similar analysis process for these events. And in addition, we recently began observations for a couple of new microlensing events identified in 2023 and 2024. We're even more excited for these new targets because we've got a couple improvements to our process for these. One of these is that we've had more frequent observations during the astrometric and around the astrometric peak of the event for some of these targets. So we have better time coverage. And in addition, we have better selection criteria for these targets. So a higher probability of these lenses being black holes because we selected for even longer timescales, and we're starting to also account for low microlensing parallax, which is another factor that can help predict high mass lenses. And then lastly, I just wanted to mention some of the overlap in work with Keck and space telescopes, which is that with Hubble recently going into reduced gyro mode, it can no longer point at our targets in the fall. So luckily, during our recent observations, we were able to fill in a couple of those and cover them with Keck, so we can still get decent time coverage on those. And there might be some potential in the future to do a similar thing with Roman as well. As a microlenser, I have to mention Roman or I think I get sued. So I had to throw that in there. I'll leave up my summary and take questions.